Good morning. My name is Chris Laughman. I'm a researcher at Mitsubishi Electric Research Laboratories. And I'd like to talk about some work today that I did with my colleague Scott Bortoff. This work builds on research that we published at the last International Modelica Conference on nonlinear state estimation using FMI. So by way of motivation, Modelica models, a lot of these models have a great deal of information embedded in them, both in the context of system behavior. There's a lot of multi-physical information which is in them, but there's also a lot of engineering time and expertise that is used to build them. And so we want to use these models for as much as we possibly can. And this value extends far beyond simulation, ranging from control to performance analysis, fault detection and diagnostics to so-called digital twins. We really want to maximize the investment in these models. So it's always important, of course, to recall that the model is not the same as the physical system. There are deviations. So what we want to do is we want to use data collected from the actual system to iteratively update the model or improve the model so that the model that we have accurately reflects the behavior of the physical system of interest. And the way that we accomplish this is by looking at estimator design. And this could be done for the purposes of estimating parameters which are difficult to measure in reality, like heat load in buildings or tire friction, or for doing other purposes such as fault detection and clogged air filters, for example. So by way of background, we have some physical system, say it's a house, and there's a number of inputs that we can measure. For example, the amount of the temperatures from a radiator or something. There might be some disturbances, people entering or leaving the space, or some unmeasured disturbances. For example, how much sunlight or solar heat gains are coming into the space. So we can measure some outputs and some that we are interested in, like the heat load, but which are unmeasurable. And then there are some outputs which we can measure, like room temperatures. So what we can do in Modelica is create a model of the same physical system. We can initialize that with some set of initial state estimates. These might be internal wall temperatures and may be inaccessible to physical measurement, but we have to take some guess. And then we can measure the output of that system. Unfortunately, the actual output may deviate significantly from the predicted output over time. And so we can end up with a situation in which, the Weasley twins at a very young age, if left uncorrected, might not turn out to be the Weasley twins that we're familiar with down the road. So instead of that, what we want to do is we want to take the measured outputs and use an estimator to take into account the predicted state and these current measurements to correct the state in our model so that the outputs hopefully measure the outputs of the model hopefully match the outputs of the physical system. So the actual output matches the predicted output. Now this is not a new idea by any stretch. And the Kalman filter provides a predictor-corrector sort of approach to working with this. This is a recursive state estimator for linear systems, assuming Gaussian errors. So for a linear time-invariant discrete time system, we can describe it with the equations on this slide with process noise and measurement noise. And this allows us to obtain estimates of the mean of the state and its covariance at each time k. So what happens here is that at every time step, first we take the model and we propagate it forward in time. So the model is allowed to evolve to the point where we get the next measurement. And at that time, so that's the predictor step. And at that next time step where we get a measurement, we then correct the state and its covariance using the measurements. So this bounces back and forth between these two steps. Now, this is all well and good for linear systems, but Modelica models are often nonlinear, or very nonlinear in some cases. And so there's a variety of approaches that we can use. The extended Kalman filter is perhaps the most straightforward in some sense approach, where we just linearize a nonlinear system around the current operating point to create the same sort of system structure. Then we can use a lot of the theory developed for the linear Kalman filter here. However, the extended Kalman filter, or EnKF, is often impractical for very large systems because the size of the full covariance matrix grows as the square of the number of states. And so the ensemble Kalman filter was designed or developed to address this issue using Monte Carlo methods to propagate a distribution or ensemble of state estimates from which we can compute the sample covariance. So we'll have an ensemble of states. We have a set of initial conditions for which we can construct the mean. Then we evolve each of those individual members of that ensemble forward. We can compute the member deviation from the ensemble mean, and from that construct the sample covariance, which can then be evolved over time. And this allows us to not actually propagate the whole full covariance matrix, which is very computationally intensive. So we want to look at these methods and compare them using Modelica. We're going to test this on a small motor model. But the challenge in doing this in Modelica is that we don't know the set of states that are chosen by the compiler. We write a model down in Modelica using declarative sort of approach, but then the Modelica compiler will compile that model to generate and select some set of states, which we won't know ahead of time. And this is a challenge because we need to know what those states are in order to design these estimators. So the approach that we use is to use the Modelica model, which is compiled to a functional Mockup unit. And at that point, the states have been chosen. So what we do is we take a Modelica model, we compile it to an FMU, and then re-import that FMU back into Modelica and modify it to create an estimator. Now, this will be demonstrated in Daimler, but it could just as easily be done in Python or other tools that have the capability to import FMUs. We can then use the linearized model evolution operator and observation operators with the FMI get directional derivatives. And this, we have to work with the co-simulation format in this case. So we're going to test this on measurements, test this estimator on measurements from the original model, which are then corrupted by Gaussian noise. And this is done again for a permanent magnet synchronous motor, the equations of which are described here and in more detail in the paper. So I'm going to make a couple of points, but rather than just talk about it, I can show you the Modelica code so that you're more familiar with it. So here is the code for the original motor model, some parameters, some other parameters describing the structure of the model, and then the states describing, or the equations describing the behavior of the system. So this original Modelica model, we then generate a functional Mockup unit from this, and then re-import it back into back into Daimler, where we get this code. And this code shows, you see that there's a very similar structure. Here's the parameters that were set, as well as the start values of the parameters, and a whole pile of code is generated automatically during the FMU import stage. And this model can then be run by just this time equals communication step size plus FMI start time. We just step forward and continue integrating the model forward in time. So this code, there's nothing sacred about this code. We can modify this and edit it as we see fit. So we're going to edit it, copy this code, and edit it to construct our EKF and EnKF. So you can see that this code is similar. This is the same start, but we add some new outputs, or rather inputs from the estimator. This is the data that we'll be receiving into the system. We have to define a new set of variables because Modelica is statically allocated. And then we can go ahead and start to construct the Jacobian, the state evolution matrix and the observation matrix, and then define the equations and propagate forward the EKF. So these equations are done here. One important point to make is that all the variables in the FMU rather, are labeled with integer tags. And so the association between the integer tags and the actual names are set forth in the model description.xml file. So you either need to parse this model description.xml file or have an implementation which maintains that association. In addition, we need to know what the states are so we can get the right variable names. And that's not apparent from this co-simulation FMU. So first, what we found works is that actually loading the model exchange FMU, getting the names of the states which are provided in that, and then using those state names and variable integer references to generate the FMU is a very useful thing to do. So then we can construct our extended Kalman filter and then run the whole system. So let me switch back to Modelica, the PowerPoint presentation. A complete implementation of this is available on Merle's website. It's free for download. So let's look at some results from this process. So we can see that The EKF and the EnKF both function very well on this small motor model. In the left-hand plot, we can see the phase currents. The black lines are the noisy phase currents, so this is what the estimator is receiving for an input. And we can see that both the EKF and the EnKF can reproduce fairly accurately the measured phase currents without all the noise from the estimates. It's interesting to note that the EKF's results are smoother, are a little bit noisier than the EnKF. But these methods also both are able to accurately reproduce the speed waveform as well. And the computational time for both these methods was certainly comparable. We then implemented these methods on a larger system, because this is really what is of interest to us, taking a large model that we built and invest time in and trying to use it for estimation. So here is a model of a building with two zones. This is actually much like a house, where there is one zone which is the main space, and then there's another zone, a plenum zone above it, which might represent your attic, for example. And there's a heat exchanger, a water-driven heat exchanger, which provides cooling to that zone and is controlled in a closed loop. So we can measure a number of different measurements: the room and plenum air temperatures, the water supply temperature, and the water return temperature. And we force the heat load to be a state so we can estimate it and add some quantization. So let's look at how this works. And so you can see these are the inputs that are, the inputs of the estimator, some of which are the inputs of the physical system, and some of which are the outputs from the physical system. So when we implemented this, the EKF worked very well. It was able to track the room temperatures very well. And it was also able to track the heat load. We made the heat load vary using in a square wave from 4 watts per meter squared to 10 watts per meter squared. You can see that the EKF tracks it very, very well, even though there's the measurements are quantized, and the fact that this is very sort of fairly challenging estimation problem. Unfortunately, the EnKF did not work as well. We found, and we were sort of surprised by this, but for reasons that became clear when we analyzed the performance a little bit more closely. And the reason is as follows. Normally what we want to do is we want to have a significant spread in the ensemble so that we can get a good estimate of the sample covariance. But at every time step, we have to perturb the ensemble to make sure the ensembles don't collapse. And when this happens, if we have these large perturbations, the perturbations end up driving the model to non-physical conditions, in particular negative humidity values, which breaks the model. So we had to shrink the size of the perturbations to the ensemble to not break the model, but that resulted in an inaccurate sample covariance, which results in poor estimates. So we found that constraint management for the EnKF was crucial for the proper estimation of these multi-physical models. So let me wrap it up. We found that these estimation approaches are very good at improving the ability of models to accurately represent the behavior of these physical systems. And that FMI is a great path to being able to use these Modelica models in an estimation context. However, it takes some effort to figure out how to use these tools, and our hope is that this presentation will help you through some of the challenges in doing this for the first time. The extended Kalman filter worked quite well for estimating the system state for a complex thermofluid model, but the ensemble Kalman filter did not work as well because of the effect of the model constraints. And so systematic approaches to associating these constraints would really improve the ability of FMI or ability of ensemble Kalman filters to be implemented in an FMI sort of context. In particular, for a small model, it would not be too hard to implement a constrained estimation method. But for large models, the ability to programmatically associate constraints with states would be very important. And so this could be an interesting direction to go for FMI standards and for FMI implementations as well. So with that, I'll conclude. I look forward to any questions that you have, and I appreciate your time in listening to this video. Again, this code is available at Merle's website for free, and if you have any questions, feel free to contact me. Thank you very much.